Good morning, good afternoon, everyone, and welcome to the second webinar of a three-part webinar series. So we are hosting a series of webinars at the Asia Oceania level, and INCOSE India chapter is very excited to be a part of this. So the second webinar is about managing variabilities, one of the topics that I am personally also very much interested in, and how do we use this to boost reuse in engineering organizations. So before I jump into introducing the speakers for today, I just want to quickly talk about INCOSE India. So next slide, please. So just to give you an idea about INCOSE, those of you who are new to INCOSE, we have overall more than 19,000 members worldwide with more than 65 plus chapters. So INCOSE India chapter is one of those chapters. And then more than 50 working groups. So these working groups are, we actually have an IW coming up this month. And then that's where all the working groups meet together and they work on advancing the science and working on different technical products. Now, INCOSE India was started in 2010, and we have about 210 individual members. And if you want to know more about us, how you can work with us, please go drop us an email or reach out to us. Now, maybe quickly going to the next slide. So I really am excited to tell you that we are hosting the Asia Oceania System Engineering Conference 2023, and this will be held between 11th to 14th of October this year in Bangalore. And we have the dates and the deadlines over here. So so this time we are not doing any abstracts, but rather complete paper submission, and that will be in 25th of Feb is the last date for the same. And you can also submit paperless presentations, and then you can check out the other details. So I would really encourage all of you to start looking at this, start making your, marking it on your calendar and start putting in your papers. And we are also planning a workshop. So the detailed agenda is available on the website. So do check out the website as well. And we will keep on updating that website with more and more detail to come. Okay, so with that, maybe coming to the next slide. So it's a great honor here to introduce the speakers for today. So we have Marco and Tim Wilkins, and I won't talk much about the session. I'll let the speakers do that. But Marco is a senior technical representative at IBM Engineering, and he'll be involved in all three webinars. And Tim Wilkins, again, no need for introduction. He's a senior MBSE expert at INCOSE, and we all love his blogs and his podcast series. So welcome, Tim, and welcome, Marco, and really appreciate your time for today. So over to you.
Okay, thank you very much. Just double check. Can you hear me well?
Yes, Marco.
Yeah.
It's perfectly fine.
Okay, very good. So,
Marco, should I share the screen or should we switch in between?
I can share the screen. I can share
and then
you
we switch?
can share. Yes, let's do like this.
Okay.
I think it's better, right?
Okay, yeah, that's good.
Good. So I guess you can see my screen now. And
yes, Marco.
Very good. So thank you again for inviting us and to kick this second part of series of webinars that we organized together with INCOSE India under the INCOSE Asia Pacific and Oceania sector. So as Mudit introduced, today we are talking about variability, in particular variant modeling or variability modeling, and how we can boost it in order, how can be used in order to boost reuse in engineering organization. Today it will be myself, and Tim. So before we quickly introduce each other, I will go through the agenda of the event. So first we have an introduction of ourselves, and so you can get a bit more an idea about what we do and who we are and where we come from in terms of background and so on. Then we have the overview of the topic of the day, that it's model-based product line engineering. So after that, we will introduce the topic of variant modeling. And then I will hand over to Tim, and Tim will illustrate and show us how we can, in practice, in action, modeling variability. And at the end, we will conclude with some takeaways for today. The presentation of today is based on the publication and article that Tim and I wrote last year, and the article got recognized as a Best Paper Award in the IS INCOSE event of 2022 in Detroit. Okay, so that's just a picture with the INCOSE president after we were awarded. So about myself, I am based in Singapore, and I lead in IBM the engineering activities for all Southeast Asia. So I have around over 10 years of experience in the field of MBSE and product line engineering. I've been always working with these two topics, and not just now in Southeast Asia, but before in Europe, so Germany, France, and then China, North America. And my previous employer, my previous organization where I developed the topic of MB-PLE was Airbus. And there I was leading the topic and I was implementing model-based product line engineering across different functions and programs within Airbus commercial, defense space, and helicopter. Now, Tim, maybe you can quickly introduce yourself.
Yeah, thank you, Marco. So I'm Tim. I'm a consultant, executive board member of OSE. We are a consultancy and training company with the headquarters in Hamburg in Germany. I worked more than 20 years in the field of MBSE, starting 2001 or 2002. And I started 2003 with the development of SysML v1. So I was a member of the team that worked on that version of the SysML. And I led the SysML task forces for SysML 1.6 and 1.7. And I'm one of the leads of the SysML v2 team. Very exciting times. So we will submit the SysML v2 next month to the OG. Yeah, and I published many books about modeling. So besides others, model-based systems architecture, which also covers the topic of variant modeling. And I'm the author of the MBSE methodology SysMod and VAMOS. VAMOS is about variant modeling with SysML. So that's me.
Thank you very much, Tim. So let's start with a video. So you will probably, there's no audio, so I will comment the video just to introduce to you guys the topic of model-based product line engineering. And this topic was basically, as I said, developed at Airbus. So this video I developed when I was at Airbus, and I publish it after on my LinkedIn. So it's online for those that want to access it. It's on my LinkedIn page, so you can access it also from there. Okay, so let's start the video. So we try to define what is MB-PLE, so the combination of product line engineering and MBSE. But what does it mean reuse model elements? So usually at Airbus, we're using a very simple example to present that. So here we can see two completely different products, but that share a lot in common, a lot of behavior, a lot of, let's say, actions, and these repeats across different products. As you can see, of course, this is like a movie software product. We would say software product line, or maybe even not software product line due to how old were these movies. But you can see that the idea is really probably not a coincidence, no? So the idea behind was really to reuse as much as possible existing artifacts and new artifacts. And this can be applied as well to MBSE and product line engineering. Okay, why is it important to combine them? Because you can boost the reusability of models, and alone with MBSE, it's much more difficult to do it. Okay, and MB-PLE use both benefits for model-based and for product line engineering. like the traceability, the consistency, but also the reuse aspect, the management of variability, and the single source of variability. You know where the variability comes from, okay? And this is just, let's say, one of the biggest advantage, the combination of both practices of model-based system engineering and product line engineering. We have defined 6 steps. First, we define the product line feature model. Then we define the product line assets with variability, the different assets like SysML models. Then we select feature configuration and we generate out of configuration 1, 2, 3, and 4, or A, B, and C, different variant product configurations. Okay, so that's a very simple approach. I will repeat this later during the presentation. And not just Airbus, but other companies like Boeing, Thales, Raytheon Technologies, Lockheed Martin are using similar approaches. Okay, so that's why it's not something practical. And this, of course, it's from when I was working at Airbus. Now I have a new email address, and I will share it later with you. So just to introduce you the topic, let's now go into more the detail of the topic, and let's start with the basic principle. So the idea of MB-PLE is how can we go from the development of SysML models, for example, but not exclusively SysML models. For today, we'll focus on SysML models, but it could be applied to test cases, could be applied to requirements, could be applied to any other type of engineering artifacts. So how we will move from the logic of these models, these assets are developed for a specific product, let's say product A, and then when we are going to develop product B, so after product A becomes a legacy product within the organization, it's just a one specific use case, but we could say that the 2 products are developed in parallel, okay? But let's take a simple use case. Product A, it's a legacy product for the organization. Now, if we want to reuse the assets like requirement, design artifacts, and realization artifacts into product B, how do we do it? So without product line engineering mechanism, we do copy and paste of assets between products. We just copy and paste. And but there is one problem with that. There's no unique source of information for common and variable assets. So once you copy it, you can create a link between the 2 things. Okay, it's called manage, clone, and own. That's better than the typical clone and own or copy and paste. However, you will not understand what is variable, what is common, and it will not be very easy to manage, and will end up to be a monstrum, this type of linking and possibility to have to manage the variation across different products that were not meant to be common or to have common parts. And then we introduce the approach that is at the base of product line engineering, at the core of product line engineering. Basically, we develop a product line, so assets for the product line. But in order to better manage these assets, we introduce the element of features, because the feature indicates where is the variability. And the feature helps us navigating across the assets, filtering the assets, and know which assets we need for product A and which assets we need for product B. So which is the biggest advantage of doing that? So we can reuse, we can manage the reuse of common assets. We know that these common assets is the same in product A and product B. And we know that there are some variable assets that are different, that can be included already here, but can also be developed ad hoc, as long as they don't conflict with the original product line. In this case, you have unique source of information for common and variable assets. So you know where the variability comes from, you know where the common parts come from, and it's much easier to manage. Okay, so that's the basic idea behind. But now we want to extend it, okay, because for today we focus on the MBSE part, so how we can apply product engineering with MBSE. So PLE can be also used not without models, not just for simple system engineering. If you manage, you want to manage requirements with variability, if you want to manage test cases with variability, if you want to manage other artifacts, software, source code with variability, it can be done, okay? However, it's when you apply it with the MBSE models, when we apply to MBSE model that, according to Tim and I, brings the biggest benefits, okay? Because already the MBSE models enables you to have the traceability, the consistency across different domains. It improve the collaboration, and they help you to manage the complexity. Now, imagine that if you don't do this just for one single product, but you do this for a product line, and you can do this, you can have traceability across between the product line and different products, member products. You can ensure the collaboration, not just between the project itself where you develop the single product A, but also in the product line project and between the out of cycle development of the product line project and the on cycle development of the member product. And you can manage the complexity, not just of a single product, but multiple products. And also the systematic reuse of the assets. So you know, as I said, where the assets are applied, where the assets are used, you know what varies. And of course, you always know where the variability comes from. Why do we have this variability? So again, MBSE and product engineering definitely improve. They are kind of a booster for each other. No? So usually what I say is that MBSE requires a huge investment, huge initial investment, and managers wants to see the return of investment. But it's not easy to see it if you apply just MBSE on one product, because the investment is high, and you start to see only from product B, C, and D. However, sometimes due to project contingencies and project constraints, you cannot develop models with variability within a project. Okay, you just focus on the models with your single project. That's why you end up not seeing really the benefits of the reuse aspect, the reuse factor, when you just do MBSE for one single project. Now, if you bring product line engineering, you already bring the variability, and you bring the management of this variability within the models. And this means also the possibility to reuse them. They are conceived to be reused across multiple products, okay? And at the same time, model-based system engineering is a booster for product line engineering, because today the different assets have a common, let's say, reference that are the features we'll see later. However, we don't have a common reference, let's say a common that could be like the model for the assets part. So MBSE brings also into the product line the model-based part, the collaboration through models that have variability. So I really see like in these two as a booster, an advantage for the others. Okay, really complementary approaches. So let's now to have a look again at what we introduced in the video of the first steps. So how is the MB-PLE approach? Okay, so let's start. We have an MB-PLE configurator that usually is a tool. Okay, now I can mention two tools. Let's mention three tools. Pure Variants, that's also used in this demonstration by Pure System. Then we have Gears by Big Lever, the most famous commercial tools. But then we have other solution too, like Feature IDE, that's more an open source solution of the University of Magdeburg in Germany. So we have, let's mention these three possible MB-PLE configurator. Then we have so first we define the product line, and the product line is defined as a feature model. So we have the feature models that represent the variability of the product lines. Okay, what is optional, what is variable, what is common, and the constraints between them. Then after we have defined the variability, that's the needs of variability, we need to implement this variability in the multiple assets. So that's why we have the multiple assets. Let's focus on the MBSE models, on the SysML models. We need to implement the variability that's been defined here and the commonality inside our assets. Okay, so we will start to develop the assets with variability, and then we start to link through variation points the features that are variable with the variable part of our MBSE assets, MBSE models. Okay, and after we do that, so we have the link between the feature model and the assets. We can select the features, and automatically, by selecting the feature configuration, we will derive the related assets that are associated to it through variation points. Okay, so we'll derive out of the product line assets the member product assets for one specific configuration. Okay, and this can be repeated n times. So this is the approach of model-based product line engineering. That's basically an extension and purely based on product line engineering mechanism approach. Now, where this approach comes from? The approach is not that Tim and I invented it, but comes from two main standards. ISO 26550, that's the, let's say, the first standards about product line, software and system product line development. And these standards was then evolved in 2021, 1.5 years ago, in the 26580. So to say it in other words, you need both standards because this lay the foundation of the methodology. And now the new standard is like a complementary standard that defines one important aspect. And the main novelty of this standard, the 26580, is that product line engineering must be feature-based. So it means that if you want to do efficient product line engineering, according to the best practice that we saw in the industry and the application of the standards in the last 12 years, we can see now that it's beneficial to have product engineering with features, not just variability built in models, in requirements, with applicability methodology and so on, but will be best to do it together with features. So based assets and with variability and features. Okay, that's the main novelty of the standard. Here is the information model of the standard, and then we can see the same mechanism that I explained before. No, so we have the feature model, we have the assets of the product line, the MB-PLE configurator, the PLE configurator. We select the feature configuration, and then we can have n member products out of the feature configuration. Okay. Let's now start to introduce the concept of variant modeling. Okay. First of all, when Tim and I thought about how can we model formally variability, okay, we know that there exist some tools, and we know that you know, you have the mechanisms. Let's say if you use pure variance or gears, you can create variation points with the assets, with your requirement, with your model. Fine, we understand the approach, right? However, how we can model the variability in a way that it's beneficial to the users and is not conflicted to SysML, for example, as a language. And so we start to set some boundaries. So, okay, which are the assumptions or boundaries that we want to set in order to be sure that you don't develop a methodology, or I would say a method, not a methodology, that that doesn't make sense, or that makes sense but has some flaws. So that's why we try to set up some rules, okay, some boundaries, we call them. So first, we come up, thanks to the experience of Tim that was involved since the beginning in SysML, and we exchange a lot about this topic. And we are, let's say, clear about the fact that SysML and product line don't really match. Okay, product line model and SysML are not really conceived, they were not born to be together. Okay, also because SysML is a system modeling language, it's not a product line modeling language. And what we say with Tim, SysML doesn't have a stereotype for a system. Okay, so it doesn't define what is a system in the language itself. We have blocks, we have parts, but we don't have system. That's why it's okay if we don't have a product line as well. Okay, so first, it's difficult to put them together. Okay, so they are not, let's say, they're not being invented to be together. The second point is that MB-PLE, it's always at the end of the day a tool discussion. Huh? So after I'm in the topic since more than 10 years, and always when I start the topic, people ask me questions about tools. Now I became a tool vendor, so even you know, even more. But anyway, I want to establish this agreement with you today, is that even if I'm a tool vendor, we try to explain, it's really a tool independent. Okay, so we want to think out of the box of the tool. Okay, so instead of always relying on the tool, at the end of the day, we need to rely on tools, but it's good to present the methodology, the method from a more abstract tool-independent perspective. Then we want to have features. So we don't want to have just assets with variability built in, but we want to have features that assist the filtering of variability, the selection of variability, the management of variability within the assets. Okay, we want that the feature become this word that we invented, the single source of variability. So for MBSE, we have single source of truth. Here we have the single source of variability. Okay, so where is the variability and where the variability come from? Finally, we have so method and tools, keep it close, keep it separate. So it's important to formalize the method first before any tool idea in mind, without not thinking which tool you are going to use. So we recommend really, and what we did also, let's define the method first. Then we will test it and practice it with one or another specific tools. Okay, so these were, let's say, the boundaries that we set before starting. And this is, let's say, the simple information model that we use to develop the methods. Okay, so just to refresh it, we have a feature model. A feature model is made by features. Okay, we have different features. Feature can be mandatory, optional, alternative, or. So you can have a group of features. You need to pick at least one of the group. When you can pick more, okay? While alternative, you need always to choose between one or the other. Then we have a feature configuration. So a feature configuration select several features, okay? With some rules, we can create a feature configuration. There is a configuration of features, okay? And then the features is linked to the variant assets, to the variable part of the assets. It means when I select the features, I can filter and unfilter, select and unselect the variant part of the assets, while the core part of the assets usually always remain the same, okay? So this is just to establish a common language terminology between us. Then after we made this brief clarification, we said, okay, now let's think about which are the possible ways that we have to model the variability. Now I introduce this, and then Tim will go into the details and will show example for it. Okay, so but let's just make it clear. So we come up with two approaches. First, we call it direct. Direct is based on the current tool-based solution. Basically, you create your 150% model. Tim will explain it better, of course, with the example. You create the variation points to the parts of your 150% model that varies. And then when you select your feature, you automatically filter out, you eliminate all the parts that you don't need. This is the direct approach, okay? The clean approach is a bit different, because the clean approach, like you build the model and in a way that the model is clean. So you can see directly from the model what is variable and what is core. You can isolate the core part, like I showed you in the information model, from the part that varies, okay? So it means that immediately looking at the model itself, you can know what is common, what is variable. You can isolate in packages the common part from the variable part. So it's really clean. There is a clean separation between its core and what between its variant. Okay, this is the main difference between the two approaches, and both approaches that are applied on the shared assets on the MBSE model, SysML models, of course, are supported by features. Okay, both approach can be supported by features. Okay. And of course, for this demonstration today, we will use pure variants. That's the tool that we used. And Rhapsody, the IBM Rhapsody, that's the tool that we use to model the variability here. Okay, so that's are the two tools that Tim now will show and will use for the demonstration. Thank you very much, Tim. So I hand over to you and I stop sharing.
Yeah. Thank you, Marco. And I start sharing with the next slide, so you should see it now. Yeah, so let's have a look on the direct and clean approach. So we are now in the shared assets model. It's not about the feature model. So I will show you how you can model variability in a SysML model. Oh, that was quick. So the important is let's start with a little warning in advance. The modeling of variance is it's not an easy modeling. That's for more experienced people. So don't be surprised if you don't understand all the details right away. And we don't have the time here in this presentation to go into on the details level. But it is my ambition that everyone takes the concepts with them. No? So we'll start with a very simple example. It's a vehicle that can have 3 different roofs: a sky roof, a standard roof, and a convertible roof. And here on the lower left side, you can see the SysML model created in Rhapsody using the direct approach. And the 3 roofs are each modeled directly as a part of the vehicle. And the parts are variation points. And as Marco mentioned, variation point is not part of the SysML language, version 1, I must say. So it's introduced by us. And these are variation points because there are some member products that don't have a standard roof, or don't have a sky roof, or don't have a convertible roof. So this is the point where it varies. By the way, it will change with SysML v2. SysML v2 will directly support variation and variance. But this presentation is now about SysML v1. The vehicle at the top now does not represent a system here. No? It represents the whole product line. So that's why we added here the stereotype product line to the vehicle block. That stereotype is also not part of SysML. Because without selecting a configuration, it says here that the vehicle has 3 roofs at the same time, which is not true. No? That's nonsense. So while the simplicity of the modeling here is an advantage of the direct approach, it is a disadvantage that without the configuration information, the model is not correct in content. No? And for example, standard model analysis do not work very well. So a calculation of the total weight of the vehicle would sum the weight of all 3 roofs. So you always need the information of the configuration stuff. Oops. So on the right side, the variability is modeled with the clean approach. And here the commonality of the variation is explicitly modeled. And the commonality of the variation is that a vehicle has a roof. That's common. And the concept of the roof is explicitly modeled and then specialized in each case to specify the different types of the roofs. So the part roof of the vehicle is now, again, the variation point, because we can change the type depending on the selected configuration. So you can see the modeling is more complex than in the direct approach. We have more model elements, and we have the generalization relationship, but the model is cleaner. So on the next slide now, we will look how to get a single configuration or member product, as it's called in the ISO 24680 standard, from these models. In the direct approach, we need a model-to-model transformation to derive the member product. So here we have chosen the convertible roof. And all other roofs and parts are removed in the transformation. And now we have a vehicle that owns 1 convertible roof. In the clean approach, well, there are 2 options how to model or how to get the member product. So here we have specialized the vehicle to convertible vehicle at the top. And the convertible vehicle now owns the convertible roof as a part. And that part redefines the common part roof that is inherited. So you already realize that it's much more sophisticated, but it's much cleaner. An alternative in the clean approach is also in model-to-model transformation that directly is applied to the variation point roof and changes the type of that property. In the asset model, the roof property has the type roof, and now a model-to-model transformation can, depending on the selected configuration, change this type to convertible roof. And of course, it makes sense then, in addition, to remove all the unused elements. So finally, we get to this simple model vehicle that owns a convertible roof. So the result is similar then to the direct approach. So it's also possible to combine the two options. In the clean approach, you can model the convertible vehicle explicitly. So you model your member product, and in addition, you apply model-to-model transformations to remove unused elements, for example. Yeah, model-to-model transformation is something that, of course, that must be supported by a tool, and that's what the common tool vendors like Pure Variance provide. So let's have a look on the model management. And we use here again the very simple vehicle example to introduce how you can organize the model. Organizing a model is not a simple task, no? And it's good to have a good organization, and there are many aspects that must be considered, including the organization of your teams and things like that. So here at the top level, there are three main packages. We have configuration, core, and variants. And the packages, or the package names, have a prefix that is derived from the parent namespace. So this is a good practice independent of the variant modeling. So here the top level is vehicle clean approach. That's the name of the top level package or namespace. And we use the short form prefix vehicle. So we have a package vehicle core or underscore core. And the core package contains all the elements that are common to all member products. And the substructure of this core package is built according to the MBSE methodology you use. So that's then independent of the variant modeling. So for example, here now we have two packages for requirements and for the architecture. So in the clean approach, now the vehicle block and the roof block are located here. Then the variant package contains sub-packages for the different variants. And each of these variant packages has substructures, again, according to your MBSE methodology. So in our example, there are packages for the different roof types here. Now we have a package for the sky roof, and a package for the standard roof, and a package for the convertible roof. And inside these packages, you have all the elements that are specific to these variants. So it is cleanly separated, and teams can work independently on the individual variants. Now, typically, you will have a team that is responsible for a convertible roof, and you have a team that is responsible for a sky roof. And if they want to change common properties, this is explicitly mapped via the core package. It can be taken into account in the engineering process. You explicitly see, oh, we change a core element. So this is something that must be considered by all the teams.
Maybe a team, can you update the slides? Because there was a it was confusing the direct and clean, and so I just changed. It was inverted, the definition. If you can update now the slides, just if you can just stop sharing and resharing, like
yes.
just go out of
sharing.
Now reshare again.
They say reshare again.
Now otherwise users can be confused. So if you can reshare.
Yeah. And share again. So here we go.
Okay, now it's correct.
You mean at the top, direct and clean was?
Yes, was
okay.
the definition. So that's why just to make it clear to
Okay.
everybody.
Yeah,
okay.
Thank you. Yeah, finally, we have here the package configuration. In the configuration package, a package or a sub-package is created for each individual configuration or member product. And this is where the model-based assembly of the configuration takes place. In our example here, this is the location of the convertible vehicle block. Okay, so this was a simple example. Let's switch to a more sophisticated example, and it's from the Airbus domain. Of course, in reality, it is typically even more complex, but this would go beyond the scope of this talk. So our example is a full-height stowage module, which is part of the cabin of an aircraft. So probably you already have seen something like that, at least from the outside. And it's a relatively simple system, and has a lot of variability. And yeah, it's not necessary that you know the details of aeronautical systems. So let's start with the feature model. So now we are outside of the SysML model, and we are in the MB-PLE configurator. And in this presentation here, we use pure variance. And this here shows the feature model of the full-height stowage. So on the left side, you can see the feature tree, and we have the features cabin attendant seat, which can be attached to the outside of the wall of such a stowage. We have a feature illumination, which means if you open a stowage compartment, then the light goes on, and if you close it, it goes off. Inside the compartment, of course, not in the cabin. Then you have a cabin crew information system. And if you have a cabin crew information system, then you cannot have a cabin attendant seat, so it conflicts that feature. Then we have different kinds of item stowage compartments. You can store standard items or trolley or wheelchair. And we have different kinds of protections outside of the stowage, high protection and standard protection. And on the right side, you can see the configurations. So the columns are the configurations. That means we have here two configurations, one with light and one without light. And the row shows the features, and the cells show which feature is selected in which configuration. So in the following, we will focus on the light feature when modeling the variance in SysML, and skip the modeling of the different item stowages, cabin attendant seat, and so forth. So we start with the clean approach and the core model. That means all the elements that are common to all configurations. And we also limit ourselves here to the structure of the system. And the same approach as presented here can, in principle, be applied to behavior and other artifacts of the SysML model. So the full-height stowage has 4 parts in the core: a stowage compartment, an electrical compartment, a stowage door, and a stowage wall. And some of the blocks here have some ports for the interaction points already defined. And well, this slide shows then the IBD, the internal block diagram of the full height stowage, which is also part of the core, of course. It shows all the connectors between the parts or ports. And you see here the boxes now are the parts. And you also see the variation point stereotype. So most of the parts here, no, all of the parts here are also variation points. So now we model the illumination or the light feature. So at the top, on the left side, you see the stowage door from the core part. And now we specialize a stowage door light. It's a special door that has a sensor that reports if the door is opened or closed in order to switch the light on or off. So we need a special door. It's a variant of the standard door. So the stowage door light is a specialization of the stowage door. So we inherit all the features of the core door, and then we add a light sensor, and we add a port for the sensor data. And also part of this variant is an interface block definition, so an interface definition of this sensor interface. So in the variant area and the variant package in our model, we have all the model elements that are specific for this variant. The internal structure of the stowage door light is shown on the right side in an IBD. Well, it's quite simple. The light, now we have the connection between the two ports, the light sensor port to the outer boundary, the stowage door port. And you can see also the wall port, which is not connected here. And the wall port, by the way, is inherited from the core door. So now we have a stowage door with a light sensor. So to install the new door model-based, we need to specialize the element above it, so the owner of the door. In this case, it is the full height stowage itself, but it's only in this example. It could also be on another level of the system. So we create a specialized full height stowage. And you see at the top, you see the full height stowage from the core, and then we specialize the full height stowage with light. So the full height stowage with light inherits all the elements from the full height stowage, including the part property stowage door. But that's the property we would like to change. So we redefine it and set a new type, which is the stowage door light. And so simply said, the full height stowage with light is here the same as the core full height stowage, but we have another door. That's what happens here in the model. So besides the special doors with the sensor, we also need other parts for the light. And this block definition diagram shows all the parts of the light variant of our example. So if you go back to our model structure, this shows all the elements in the variant package for the light. And they are clearly separated from the core. So we have the special full height stowage with the light, which is more the assembly of all the special elements. Then we have our stowage door with the light. We have the stowage light module, which has the light itself and controls it. We need a special wall. There's a mount and different ports for the light in the wall. So we need a stowage wall for light. And we need a special electrical compartment which also has ports and other infrastructures for the light. And the modeling of these special walls, electrical compartments, etc., works the same as for the door. We specialize the core element and we redefine the parts, but all the details are not shown here now in this talk. I only demonstrated it for the door. And well, here's the internal structure of the full height stowage then with the light in an IVD that depicts the connections between the parts. So we also have the connections between the parts, or specifically the ports of the parts. There are also other elements which are not shown here. For example, the storage compartment, because we focus here on the light feature. But there are more elements than depicted here in the IVD. Yeah, so that's the clean approach. Let's switch to the direct approach. It's the same example. And unlike the clean approach, now there's no general concept of the different parts. So all parts are modeled directly. That's why we named it direct approach. No? So for example, the storage door here on the right side already has a light sensor part. And the electrical compartment has already the ports for the light and so forth. So everything is modeled directly without extracting the common parts and specializing and all these things. So there are many variation points here. And to avoid cluttering the diagram with stereotype names, which is a lot of text, the little VP symbols here annotate the variation points. And this is not part of the diagram. It's not part of Rhapsody. I added this on this slide in the presentation. But this is only to simplify the visualization here. Otherwise, we would have a lot of variation point names in the diagram, and that clutters everything. So this diagram illustrates very well well, on one side, the advantage, and on the other side, also the disadvantage of the direct approach. It's much simpler than the clean approach, much less elements, and it's where you model it directly, yeah, like you think it. It's, oh, I need this, whoops, put it in the model. But the disadvantage is that the information about a single variant like the light is scattered in the model. And you see all these variation points here. So there's no clean separation of the variant aspects from the other one. And this can lead to many problems. Something is overlooked when there are changes. There are conflicts because different people have different access rights for different elements. So maybe there's a storage door team and an electrical compartment team. So we have different teams, and you are responsible for the light. So, you must talk to all of them. And the model does not provide a clear view on the light feature and so on. So, yeah, of course, we also have an internal structure. That's the internal structure of the full height storage model with the direct approach. And well, it shows everything in there. So it's not the presentation of a single member product. That's a presentation of the product line, and you need the model-to-model transformation to extract all the elements you don't want to have for this single member product. Yeah, let's finally compare both approaches, clean and direct. So there's not this common assessment is, oh, clean is better than direct, or vice versa. So it depends. As usual, it depends. Yeah, these are two tools, and it depends on the current situation which one is the best tool. You should not have in the toolbox only a hammer. You need different kinds of tools for different situations. So in the clean approach, there are many specializations that need to be modeled. That costs a lot of more effort and more modeling skills. But well, it can pay off if you need modularity in your model. Like, it's more a plug and play model then. this separation of these concerns, in our vehicle example, that you extract, oh, we have, but what we have in common that the vehicle is a roof, things like that, that requires a good thinking through these concepts. What's really the common part, which is the special part, which can pay off in the long term. It's always good to think through concepts. Well, in the clean approach, the effort increases with the number of variants. That's also the case for other approaches, but here it's more prominent. So this requires and promotes that product configurations are thought through and defined in advance. Now, you cannot consider all the possible product configurations. You must in advance define, okay, I have only this, this, and that. Well, in that advantage is now you have the clean separation of core and variant elements. Now, separation of concerns is a common advantage in architecting. In the direct approach, it's less costly, and it's suitable, for example, in the very early phase to evaluate different variants. So if you do some trade-offs, then it often does not make sense to spend a lot of effort and to make it clean. It's more quick and dirty, try and error, and so then you can very good use the direct approach, for example. And well, the disadvantage that everything is together in a single model. We have a car with 3 roofs and things like that. The advantage of it, it's a comprehensive view of all the interfaces and connections in the model. So it can become overcrowded with the increasing number of variants, but you see everything in one single place, which is also a good advantage. And well, you can start with direct to elaborate your system or your product line, and later you can transfer it to clean. So it's not a dead end. Yeah, and with that, I hand over to Marco for the conclusion. I think it's only one slide, so we can just click and
yes,
you take this slide.
Conclusion, very easy, and just a summary of what Tim and myself illustrated today. Thanks a lot, Tim, by the way. Very clear and exhaustive. And so first, try to follow existing standards. You want to apply this in your organization. So of course, don't reinvent this famous wheel that everybody mentioned, and try to reuse the existing standard. Start from the standard that we provided to you, for example. Okay, that's the first point. Second point is try to detach the discussion from the tool. Okay, and this is said from a tool vendor. Okay, so think about the method first. Think about what SysML language can do. Think about now of course there will be SysML v2 that will introduce, as Tim said, the variation concept, the variant element, and that's why it would be a new starting point to enhance the methodology. Now we started from SysML v1, and we saw, okay, how can we model the variability from a method perspective according to SysML without conflict with SysML, and so on and so forth. Then, of course, you need to talk to all the stakeholders. Okay, so if you are developing this in your organization, don't just develop the method and push it top down, but discuss with other stakeholders, discuss with people that deal with modeling every day and deal with project development, product line development, and try to adapt the language for the needs. Maybe this specific project needs the direct approach, or maybe it needs the clean, or maybe needs a combination of both, for example. Okay. Then we recommend, we didn't talk today about the framework, but we recommend to support the MB-PLE adoption in your organization with a framework. So you need a process based on standards, you need a method, that's, for example, the clean or the direct or a combination of both. You need an information model, so which are the elements that you are going to use. Then you need a tool chain, of course. And finally, you need the people, you need the environment where you want to develop it, the proof of concept where you want to test it, and so on and so forth. So to conclude, drive the tools, don't let them drive you, said by a tool vendor, so it even increases importance, okay? Think first before jumping directly into any tool, any solution, okay? That's it from our side, and if there are some questions, we can pick them. We will exceed maybe some minutes, but there are some
Yes,
questions we can pick up.
Thank you, Marco and Tim, for your insightful session on this. We have a couple of questions, Marco and Tim. Maybe anyone can take it. So the first, I'll read out the two questions. Maybe you can answer it. The first question is, what modeling method do you use in the embedded systems domain? And in line with that, are there any approaches to define and creating modeling methods for languages as UML and SysML?
So I can start with the first team. Maybe you can take the second.
Okay.
I can start the first because, as probably some of you knows, we had the first webinar of this series with Continental. Continental, Enrico Seidel, that was my say webinar partner at that time, is also using a variability approach. The variability approach that you use, because he showed it to me, it's very similar to the clean approach, for example, of the team shows. Not exactly the same, but very, very similar. I would say 90% similar to the clean approach of team. So it means that it is that for the development of embedded system, that's what it does, so ECU development, this approach fits better than that's the other one, because the direct, because probably they search for more modular, see, they have more modular systems, and that's why they want to keep separate what is core and what varies. So this was the main concern. And for these specific needs of Continental, I can mention that they prefer the clean. Okay. However, I would not be surprised if other companies use the direct for embedded system. I think it's really a question that you need to ask yourself, and once you practice it, you will see. Could be also that you apply both, depending on the development state of your embedded system, as a team mentioned before. So it's really like it's difficult to answer because it really depends on the phase of the project where you are, on the needs that you have, on the complexity of the product, and so on. For too many factors.
Yeah. Thank you, Marco.
Yeah, and the second question, are there any approaches to define and create modeling methods for language and UML and SysML? Well, yes, there are, and it's quite similar of creating a model for a system. So eat your own dog food. First, you should define, of course, the purpose of the method. That's very, very important to do that. And then, identify your stakeholders, the requirement for this method, and so forth, use cases. And then an important artifact is that you create a concept model first. So what are the concepts behind this method? Now, we for example, a requirement. We would like to define a method for requirements. So what is a requirement? Well, in our focus here, and what are the properties of a requirements and how it's related to architecture elements and so forth. And then you get a concept model. And with this concept model, then you can derive the stereotypes, or in more general, the language extension for UML and SysML. So that's simply said the approach how you can create a modeling method. But the important thing is start with the purpose.
Yeah. Thank you, Tim. I think one more question has popped up, Tim, for you. Where can I find end-to-end USEM, WSEM, that is our methodology examples? Unlike magic grids, it's really difficult to find practical USEM implementations.
Yeah. So, well, OSEM, although the name is quite similar, I have different methods. OSEM is the object-oriented systems engineering methodology, which is so I have nothing to do with OSEM. I know that, but it's not the OSEM methodology. So if the question is really about OSEM, unfortunately, there's not so much information available. There's a web page on the INCOSE site, incose.org, from the OSEM working group, and there you find some entry points to OSEM, but I think mainly about the definition of OSEM and not OSEM examples.
But maybe Team it's famous because it's one of the creator of SysML that is, I would say, even more detailed and more applicable than OSEM. So it's more practical, I would say. Okay, so than OSEM. And there you have books, you have a lot of sort of resources, I think, Team, that you could.
Yes, and an example. So for it's available for the Cameo products. There's a plugin. Type it in the chat. I hope it's correct. I have not double checked it, but there's a plugin for the Cameo suites, and inside this plugin are also sample projects and also a Wamos sample project. And
then as on the IBM side, so we are releasing Harmony 2, so 2.0. So we have the new version of Harmony. Okay, so it means that it takes into account more the system development than before. So that's why if you are interested about that, you can also contact me. I can provide you information about that.
One last question we'll take, Marco and team. If hope you are okay for that. I won't take more than 5 minutes. So what are the changes we need to apply when we go for clean approach, then direct approach, or even classical MBSE application?
So transition from one to another, I guess, right?
Yeah.
Okay.
Atmanand, if you can have more details, you can unmute and you can ask the question, or you can explain in more detail what exactly you're looking for. I think you mean to say that from traditional to classical MBSE application, or what changes we need to do when we go for either clean or the direct approach?
So I think teammates, if you develop a direct approach, then you want to move to clean. Or if you have a model without variability and you want to reuse the model and add the variability on top. So probably this I understood from the question.
So, well, for example, if you would like to go from direct to clean, then you must extract the commonalities from the model. As I showed you with the simple vehicle example, you typically do not go from clean to direct. I think that does not make sense to do that. And if you have the classical MBSE application, so I think a classical MBSE application is here a SysML model for a single system. Well, the starting point is the feature model then. So you typically start outside of the SysML model with the features, and then you have your features, and then you can start introducing the variability in the SysML model. And if you have the direct approach, then you just add the variant features to your model. And if you have the clean approach, again, you extract the commonality and do the specialization stuff.
And if I can add the team, even if I find the clean more complete and more, let's say, cleaner, let's say, no? So in the definition of variant and core, and if you have legacy artifact, legacy model, it's much easier to apply the direct if you want to apply the variability on the assets. Now, again, now after you apply it, the direct, maybe a good transition could be you have your legacy model without variability, you apply the direct, and then once you are happy with that, you can slowly move to the clean. It could be a smooth transition if you want to go from a legacy product with system model without variability into the direct and then into the clean. And you can even decide that just one part of the model you will move into the clean and another part it will stay direct because you don't need it, because it's abstract, is the functional layer, and you want to do more the technical layers because also we have layers, no? So, and that's, we just didn't mention that. But and,
that's important. And you can mix both approaches, no? It's not pure clean or pure direct, you can do both.
If I can mention something from Airbus, I think we mentioned many times, and it's public knowledge. We basically used for the functional layer, the clean at Airbus, but then for the technical layers, we use clean and direct, but people prefer to use the clean, let's say, for the technical. I received one additional question in my private box. Maybe this then I don't know if I need to. I think it can be answered. I can just read it out. I can just copy and paste, and then we can conclude, I guess, right?
Yeah. Yes, Marco.
So I just received it in my private. So this was the question from Manad. Sorry if I pronounced it in the wrong way. So does MB-PLE can be applied to production where just 10, 15 products per year are produced? Example, military aircraft in different sectors. I think it would be really good if it's applied in such a context, because I imagine that these 10, 15 military products don't have so many differences. So there is for sure a very huge potential of reuse. It would be much more efficient if you are develop 10, 15 products. Wait, I think here it's products probably is not variants. It's I guess it's like a batch of product, number of products. You need to correct me if it's right or wrong, my interpretation. So you mean like numbers, so really 10 physical products or 10, 15 different variants, because this is also different. Huh? So if you produce just 10, 15 products and they look quite similar, maybe it doesn't make so much sense to apply the MB-PLE approach, right? But if these 15 products that you produce that are quite complex have a differentiation, have variability in it, and they have common parts, then I would recommend, even if you have just 15 products per year, because they are complex products, so you will improve your way of working. So that's what I can tell you.
Mm-hmm.
Okay, so I think we are through.
Yeah. Thank you, Marco. Thank you, Tim, for your time and sharing this your learnings and interesting topic. I hope all the participants had good learning opportunity. And we once again thank everyone for your time. And if any questions or anything, you can reach out to Marco or Tim. They have given the email ID, or even you can reach out to INCOSE India, where we would help you to answer your queries or you address your queries.